So if we put another north pole into the magnetic field between the poles of this horseshoe magnet, the north pole will be pushed downwards, whereas if we put the south pole of the other magnet in, it will be pushed upwards. The direction of the force on a current carrying wire is given by Fleming's left-hand rule. In this situation we have a current to the right and a magnetic field pointing downwards, which means the wire will be pushed into the page. We can also calculate the size of this force using this formula, where B is the magnetic flux density, I is the current, L is the length of wire in the field, and theta is the angle between the wire and the field lines. This assumes that the magnetic field is uniform. If instead we have a charged particle moving in a magnetic field, then the formula turns into this. And if the particle is moving perpendicular to the field, then we get this, which is the version shown on your formula sheet. So if we have protons moving to the right through the field, the force will be into the page. If we have electrons moving to the right, the force will be out of the page. If we have a current flowing to the right, that's the force into the page again. Or if we had electrons flowing to the left, which of course is what's actually happening in the wire, that's force into the page as well. Obviously they have to be the same. Okay, so to recap, electric fields push positive charges in the direction of the field lines, and they push negative charges in the opposite direction to the field lines. Magnetic fields only push charges that are moving not parallel to the field lines. Magnetic fields push particles perpendicular to the field lines, as shown by Fleming's left-hand rule. Pause the video now and play the simulation game for a bit until you are happy working out which direction the particle will get pushed in each situation. Now imagine a magnetic field into the page and an electric field downwards, making them perpendicular to each other. Positive particles are fired in moving to the right, perpendicular to both fields. Pause the video and work out which way each field will push the particles. Hopefully you'll have found that the electric field pushes the particle downwards and the magnetic field pushes the particle upwards. We're now going to ignore gravity. This is a totally fine approximation because the particles are going to be moving so quickly they will appear to move horizontally when the electric and magnetic fields are switched off. Let's suppose that all the particles are moving with the same velocity, v. Now, if we adjust the electric and magnetic field strengths until the two fields push with equal forces on the particles, all the particles will still move horizontally and come out the hole on the other side. Pause the video now and try to write this idea down in a formula that the electric and magnetic forces are of equal size. You should get this, and so simplifying we get this, and this tells us the velocity of the particles. Now imagine we had particles with lots of different velocities. Some will be pushed with a greater force by the magnetic field, and these will be deflected upwards, while some will be pushed with a greater force by the electric field, and these will be deflected downwards. Only the particles that are pushed by the two fields equally will remain horizontal and come out the hole at the other side. That's why this contraption is called a velocity selector. You can adjust the strengths of the fields according to this formula to only have particles with a particular velocity coming out the hole. Now imagine the same situation, except that the electric and magnetic fields are pointing in the same direction. The charges will follow a looping path. Use Fleming's left-hand rule to convince yourself that this is correct. And finally, ditch the electric fields completely and just imagine a magnetic field and nothing else. We know that if a charged particle enters a magnetic field moving perpendicular to the field, the magnetic force will be perpendicular to the particle's velocity. Assuming there are no other forces on the particle, this means the particle is going to travel in a circle, with the centripetal force equal to the magnetic force. Try writing this as a formula. You should have this, which we can simplify to this. Rearranging like this allows us to see how big the circle will be and that it depends on the mass, charge and velocity of the particle and on B, the magnetic flux density. This is what's going on inside the two semicircular halves of a circular accelerator, often called a cyclotron or a synchrotron. Meanwhile, electric fields are used to accelerate the particles across the gaps every half turn. And that's the end of the magnetic forces section. Take another break now to do the second Google Forms quiz.